here. So, good afternoon, everyone. Let's start today's seminar. So, please share your screen first. Okay, good. Let's start today's seminar. Today's speaker is Jaeok Yi from KAIST. He'll talk about sub-frequency search at a laser as a signal of dark matter sector particle. Please start.
Thank you for the invitation and organization. I'm very glad to introduce our recent results. And it is a kind of proposal of new ways for dark matter search. And this talk is based on the letter with the same title written by me, Haesung Lee, and Jian Lee. And this is an archive number for your reference. So this is an overview of my talk. I will begin my talk with a brief introduction and a short review of the light shining through walls experiment. Then I will talk about the motivation and setup of our new experiment. After that, I will explain our model, which can be constrained by our experiment. Discussions, including result, will follow, and I will finish my talk with a summary. Since I got a bad cold recently and I have a sore throat, so you might misunderstand my words. And my talk won't be so long since it is based on the short letter paper. So if you have any questions or discussion, then don't hesitate to interrupt me. Okay, let's begin. Introduction. I believe all of you are familiar with this figure, so I will explain it briefly. The standard model, the most successful model in physics, only can explain 5% of the energy component of our universe. It is believed that dark energy related to accelerating expansion of our universe accounts for 70% of energy component, and dark matter related to the galaxy rotational curve, etc., accounts for the other 25%. So physicists want to explain dark matter or get some hint of dark matter. So there are many dark matter candidates. So for example, WIMP, primordial black holes, gravitinos, and stellar neutrinos, etc. Among these candidates, I am interested in some light candidates which possibly interact with photon. Examples of these candidates are axion or axion-like particle or dark photon, etc. And these candidates are popular in these days, therefore several experiments for their detection are proposed. Among these experiments, I want to talk about lighting shining through wall experiment or simply LSW experiment. Okay. So the interaction between dark matter and photon makes it possible that dark matter can be produced from the photon. In this case, a laser, or easily speaking, a high-power photon generator, can become the source of the dark matter. So, and if you shine the laser to the wall, then light or photon is blocked by the wall, but dark matter produced by this photon can penetrate the wall. So this penetrated dark matter can generate another photon over the wall, so light signal can be detected over the wall. So I will explain it with this figure. This figure describes action search by LSW experiment. Shoot the laser to the wall from the left side, and by applying a magnetic field, this laser light can be converted to action or action-like particle through action photon, or simply action photon motor. And these actions can penetrate the wall, and applying a magnetic field on the other side, these actions are reconverted to photon. By locating a photon detector on the right side, we might detect this signal. Or this procedure can be described by this Feynman diagram. So simply speaking, physicists are staring at the wall, waiting for a photon signal to detect dark matter. This is a kind of crude summary of LSW experiment. So using LSW experiment, we can constrain the parameter space of axion-like particle. So this figure is a constraint for axion-like particle. Oh, okay, axion-like particle. Apples the abbreviation abbreviation of any bright particle search, is the most precise LSW experiment so far. So it gives this red line gives the most strong constraint. Also, I want to also mention gamma, gam, gamma 5, which is another LSW experiment, which corresponds to this green line, green region. And this is another LSW experiment. So we compared our new experiment setup with these two experiments. Also, right guys, LSW experiments can work for the detection of dark photon. Dark photons can be created by the laser via kinetic mixing, and vice versa, photon can be created from dark photon. So using this kinetic mixing, we can construct LSW experiments like Axion search, and this figure is the constraint of dark photon parameter space via light shining through wall experiment. As in the Axion-like particle case, R plus gives the most strong constraint. Okay. And I want to show the picture of describing ALPS2. It is a new version of R plus and it is on construction. And you can check that its final stage of ALPS-C, it has very huge size. Its length is about 20 meters and it is much more bigger than output. And it uses much more sensitive detector, so its sensitivity to dark matter sector will be much better than ARPS and gamma 5. Okay. So far, I've talked about known results from previous research based, especially light shining through wall experiment. Now I want to talk about our work. Oh, sorry. Okay, the motivation of our research can be summarized in one sentence. Okay, what if the dark matter decays to another dark matter and photon? Okay, look at this figure, look at this Feynman diagram. Suppose photon from the laser is converted to dark matter X, and X does penetrate the wall, like usual LSW experiment setup. However, what if suppose X decays to another dark matter X prime and emit a new photon, then what kind of things happen? So I want to talk about this decay qualitatively. So let's talk about its kinematic in detail. First of all, the frequency of this emitted photon will be less than the frequency of the laser. So we call it sub-frequency signal or sub-frequency photon. Okay, so I want to describe its kinematics with this figure. So consider the rest frame of X. Then in the rest frame, there is no directional preference. So thus this sub-frequency photon will be emitted isotropically. But if in the red frame X is boosted, okay, so if X is boosted very much, these photons are concentrated on the direction of boost. However, in the lowly boosted case, these photons are still spread. Okay, so let me say it again. In the rest frame, decay occurs isotropically, but if X is highly boosted or its energy is much larger than its mass, then this sub-frequency photon is highly focused around the direction of boost. But if the energy of X is comparable to its mass, then sub-frequency photon can be spread in various directions. So in a highly boosted case, then usual LSW experiment can detect this phenomena because since the sub-frequency photon is focused on the direction of its boost, this sub-frequency signal can arrive at the detector. However, the size of detector is finite, so if in the lowly boosted case, these photons can be spread, and so this sub-frequency signal cannot reach the detector. Okay. So simply speaking, this poor cat or this species is staring at the wall. So, but the light does come out the wall, but it does not reach our eyes due to its spread limit. So simply speaking, the problem is that we need to gather this signal. How can we do that? Okay. We adopt a very simple idea, just wear a scope or equivalently use a waveguide. Waveguide, for example, optical fiber in optics, uh, in optics experiment can gather the signal. So by installing a waveguide between the world and eyes, the cat can find photon signal, or physicists can detect the photon signal or dark matter signal. So we suggest a waveguide that can collect and guide all the folding sub-frequency signal. So long, like this figure, or long pipe with the inside coated by a highly reflective metal or mirror would be suitable, or optical fiber in optic experiment can be used too. So we assume that the reflectivity is sufficiently high to neglect the signal load. So it will save at least half of the signal. Okay. Now let's visit the setup of our new experiment, and this is a pictorial description of our new experiment setup. Place laser cavity and mirror over the wall and photon detector like usual LSW experiment. The cavity is used to amplify the laser signal. And the bluely shaded region represents the waveguide for signal collection, as I described before. So our setup is basically equivalent to the setup of outputs to except for 2 points. First of all, as I explained, waveguide is introduced to collect sub-frequency signal, and we vary the length from the detector to the wall. As we've seen before, the length from the detector to the wall in output 2 is 100 meter. We studied the setup with the same 100 meter length. However, we also studied the setup with a 1 meter length to consider a tabletop experiment. Okay. So this is the motivation and setup of our research, and we constrain the specific example of this specific example using this experiment. So I want to introduce our new physics. So our new physics uses vector photon and dark action photon. Through the vector photon and the dark action photon, decay I described before can occur. So the relevant part of the Lagrangian in the mass eigenstates given like this, and the below Feynman diagram shows how this decay can happen. The left figure is the usual laser in the standard model, describing usual laser in standard model, and the right figure represents our new physics. Okay. Vector photon is a kinetic mixing between U1 QED and U1 dark, or kinetic mixing between photon and dark photon. So this vector photon make it possible the photon can be converted to dark photon. Okay, and this dark photon can penetrate the wall, and the dark action photon is an action photon dark photon vortex, and it makes it possible that the decay into the photon. It makes it possible that dark photon can decay into the photon and action, like this Feynman diagram. So this decay describes the decay I've explained before. So our experiment can constrain this parameter space of this new physics. Let me show some detailed calculation. So consider a laser with flux and gamma and frequency omega. Then a dark photon with mass smaller than omega is produced with power epsilon square and gamma. Then in the presence of the light action, the dark photon may decay into a photon and an action with a decay rate given like this. Okay. And so the number flux of the sub-frequency signal photon after propagation of distance L is given like this. Okay. And that it is just a simple calculation. And to simplify the situation, we assume these two conditions. First condition is the mass of axion is much smaller than that of a dark photon, and the term in this exponent is much smaller than 1, so it's sufficiently small. This second condition is valid unless the mass of dark photon is very close to frequency of laser. And in our simple setup, the signal photon flux is simplified with this formula. And in this case, two couplings are product merged and can be thought as a new effective coupling K. And also it is proportional to L since it is a decay process and L becomes larger, then there are plenty time for decay. So, and after that, I want to mention some technical detail and detected flux. So the flux detected in detector is given by the detected flux is proportional to the number flux of subfrequency photon with constant eta, and it is given by the product of eta cavity, eta kinematic, eta effective efficiency. Sorry, and eta cavity is the cavity amplification ratio from the fabric part of cavity, and it amplifies the number of photons reaching the wall. Since we use the same, we assume the same cavity and same laser of ALPS2, we take the same eta cavity as ALPS2. And eta kinematic is the probability that the subfrequency photon reach the detector. This plot shows the eta kinetic in various LSW experiments and our setup. You can check that the probability decreases as the mass of X becomes bigger, because it becomes closer to less frame, then its angular dispersion becomes much larger. Especially ALPS2, which is the ongoing new LSW experiment, gives a much smaller probability than the other two previous experiments, because the size of detector size of ALPS2 is very small, so its probability are very small too. And okay, and the blue line on the top is corresponding to our waveguide experiment. Introducing waveguide gives much larger eta kinematic than other LSW experiment, so our setup is much more sensitive to this model than usual LSW experiment. Also, eta efficiency is the efficiency factor of detector, and if ALPS2 or other LSW experiment, target frequency of the detector is focused on the laser frequency. So due to the low frequency of signal, eta efficiency of our setup is smaller than that of ALPS2. We compute the average eta efficiency in sub-frequency interval, and each value is about 0.54, and it is about 54%. So it is small, but it still works. So we use same detector as ALPS2. And finally, using this detected flux, we can compute the signal to noise ratio in the detector. And the signal to noise ratio is given by this formula, and D is the number of dark current, and TS is total measurement time. And we take the same ND and TS as ALPS2, and using this as NL, we can constrain our scenario. So I describe our motivation, our setup, and our scenario. So now we want to show our constraint. Now I want to mention discussions including results. So okay, this is the constraint and sensitivity plot of K and the mass of dark photon. two blue lines shows the sensitivity corresponding to our new experiment. And we also showed the constraint from other LSW experiments, gamma 5 and ARPS. And also we included the sensitivity plot of ARPS 2. Okay. Despite the angular dispersion, ARPS 2 shows much better sensitivity than other previous LSW experiments. The reason is because ARPS2 has a much huge size and its detector is much more sensitive. And however, our setup shows much better result than other LSW experiments. So our new setup introduced Waveguide and it results in a huge increase of eta kinematic. So the new setup with Waveguide can excel the early LSW experiment by orders of magnitude. And this solid line is 100-meter experiment, which is identical to ALPS2, and this dotted line is 1-meter length experiment, which is considered as a tabletop experiment. And this tabletop experiment can outperform other LSW experiments and even ALPS2 in high mass region. So, and in the high mass region, especially using a waveguide for a given L significantly improves the sensitivity. Since in the high mass region, the left frame is close to rest frame, so its dispersion is larger. So our sensitivity is much better than other LSW experiments. Okay. So I just write the how to increase the sensitivity of our experiment, increasing the size or increasing laser flux or cavity quality or increasing efficiency or varying target frequency, and basically decreasing noise or increasing measurement time will significantly increase the sensitivity. So our setup can be improved. And okay. And for the remaining part of this talk, I want to emphasize the difference between our scenario and other scenarios that LSW experiment usually deal with. And our new setup looks very similar to LSW experiment, just we introduced a waveguide. However, our underlying new physics is much more interesting, as I think. Instead of using waveguide, we might vary the location of detector to detect angular dispersion in our scenario. So in this case, there is no need of word in principle. So what I want to insist is that our experiment is different from LSW experiment. And I want to discuss about dispersive property of our scenario in detail. Okay, since the energy of dark photon in left frame is same as the laser frequency, the left frame is boosted with the velocity beta respect to the left frame, and beta is given like this. Then the energy of subfrequency photon and polar angle is given like this. Okay, then you can check that if beta is close to 1, then theta L goes approximately 0, and if beta is close to 0, then theta R is close to theta L. Then it shows the angular dispersion, and we can check the angular dispersion works. But what I want to emphasize is that EL, so the energy of subfrequency, is also distributed around omega over 2. Okay, omega over 2. And the energy dispersion is another important consequence of our physics. So I want to show some figure. So this left as I explained before, this left diagram is standard model, and this right diagram is our new physics. And sorry. Suppose there is a photon emission with this spectrum. So centered at omega and this type of spectrum. Then our scenario suggests the additional photon with subfrequency spectrum should be emitted. So if there is a spectrum with like this shape, then there should be another effect like this. So then the essential part of this scenario is that any source of light can produce sub-frequency light as a signal of new physics. Since there are plenty of possible extensions such as microwave cavity, X-ray light source, isotope spectrum, or astrophysical data, and these spectrum, if our new physics are exist, if our new physics are exist, then these all light source also should emit sub-frequency photon. So there are many possible extensions of our experiment or our scenario, and also the test of the combined coupling K cannot be obtained just by multiplying the bounds on vector photon and dark action photon obtained independently, because previous constraints on these two parameter space does not consider the combined effect we suggested. So if this decay type of new physics can happen, then these bounds must be reconsidered and revisited. So we need a dedicated study for the implication and constraints of the combined photon K. And in this sense, we think that it can be taken as a practically new photon, which names the frequency photon. Okay. Then let me summarize my talk. Okay, my talk was so short. And interaction between dark matter and photon might make it possible that dark matter produced by photon can decay into another photon. We suggested an experiment using laser for examination of this new physics, but any source of light besides laser can produce a frequency light as a signal of new physics. So many possible experiments can be exist, and we need a dedicated study for the implication and constraints of the sub-frequency photon, and so rich physics implication from you are warranted. Thank you for listening. And do you have any question?
I have a question.
Yeah.
So in your scenario, the photon loses its energy spontaneously, right?
Yeah.
So I wonder the mean free path of the photon
Which
to have the sensitivity for your experiment.
You mean in the waveguide, the mean free path of sub-frequency photon?
Any photon will lose its energy, right, in your scenario?
Yeah.
So question is how long it can propagate before losing its energy?
So because I'm not good at optics, so I don't know about technical details about the scenario, but maybe so. I think we need to to forbid that, we need to increase our energy or number of photons to increase signals. And so we assumed just that waveguide gives no energy loss, so it is just assumption. But you are right, so mean field is finite, so maybe to consider the mean free path, we need some technical details of waveguide, but we didn't care about that now.
Just my naive estimation, if you assume 1 meter long waveguide,
yeah,
I guess you cannot have very long mean free path, right, to have size of a signal.
Yeah.
Is it correct? If it is so, I wonder if CMB already ruled out your scenario or not. Cosmological distance propagation of photons.
Jaeok, I think that what Professor Park is asking is, whether any photon actually loses the energy. I think you want to explain that it is not the original photon that decays into another photon. It is the dark photon that can be also generated besides the original photon, and it decays into a photon.
Yeah, so I guess you can calculate the mean free path of the photon, right, in your scenario, considering
it's not the mean free path of
parameter.
it's not the mean free path of the photon. The original photon does not decay. We just pointed out whenever there is a photon, the light source that can produce a photon, it can also produce the dark photon, which is massive. And I mean, in assuming the kinetic mixing, and that dark photon, that heavy one, can decay into photon. So we are not talking about the mean free path of the original photon.
I mean, when you have a k parameter, non-zero k parameter,
Yes.
you can easily calculate the photon to sub-frequency photon conversion rate, right? So your k parameter determine the conversion rate of photon to sub-frequency photon. I guess that's what you are looking for, no?
The conversion rate. I'm not sure if I'm following the term, but I mean this is not really the. I mean at the mass eigenstate, it is the dark photon that's generated, not the photon.
Yeah, just look at the Feynman diagram here.
Yes.
So consider
Yes.
whatever the photon you have. Then
Yes.
by epsilon and g, you make the original photon to convert into the sub-frequency photon and Axion. So by having this process, your original photon loses its energy.
No, it's not I mean, to talk about the energy, we have to go to the mass eigenstate, and I'm trying to point out that the Feynman diagram in the right side is just the interaction eigenstate. If you go to the physical eigenstate, the mass eigenstate, what is really generated is the dark photon with a suppression factor epsilon, which is heavy one, and that one decays. It's not like the photon decays into another photon.
I guess the same diagram describes the photon to sub-frequency photon conversion. No?
Well, depending on how you define the conversion.
Yeah, just allow epsilon and g.
Yes.
Then you have the diagram, photon to photon and Axion. That is described by k parameter you defined, epsilon times g a gamma gamma prime.
Yeah, maybe I don't know if I thought about that one seriously. So you're thinking about some photon oscillating into a dark photon and it decays into thing. Okay, I'm a little confused actually, I should say, but we will think about it. I still don't think it is not the right way to think of the photon decaying into the another photon plus action, but yeah, we will think about it more.
Okay, thank you.
Any other questions or comments? I have some naive questions. So usually we think about the axion photon conversion, we need magnetic field, right? But I mean, in this case, I mean, gamma prime gamma axion case, we don't need any background magnetic field also.
Yeah. Photon can be converted action and gamma through the action portal, and details are in this below paper, Kaneta and Hasan-Reed wrote, and there is if the quark is both charged under ion dark and ion QED, then this phenomena can happen. So,
I have one more question. So your model have two coupling with, I mean, standard model to dark matter and dark matter, two standard model to dark matter. I mean, your case is suppressed by two, but this same, sorry, maybe I'm confusing. Same with the user case. I see. Sorry, that's fine, that's fine. Any other questions?
I just gave a slight more talk about Professor Park's question, and I still don't think it is just the right way to think about the. I mean, we cannot really think about the oscillation and the mass against state at the same time. The oscillation is only for the interaction against state, and when we talk about the decay and the decay of the heavy particle to light particle, we have to strictly stick to the mass against state basis, not the interaction against state basis. So in that sense, we cannot really think about the conversion of the usual photon into a sub-frequency photon in the action. That's how I think. I mean, you can
think
take every.
Forbidden, or I guess it is allowed.
It's forbidden. No, I don't think so. No, I don't think so. I mean, you can stick to only either interaction against it or mass against it. And the best way to think about the, I mean, you can choose anyone. But I think the best way to think about this decay process is the mass against state. And when you think about the mass against state, there is no oscillation. It's just the massless photon and the massive dark photon. And the massive dark photon is generated with the suppression factor, and it decays very slowly. That's how I say.
So you're saying the process is forbidden by.
It's forbidden.
By,
I mean, it doesn't happen. It doesn't happen.
Forbidden by forbidden by what?
I mean, as I mentioned, that we have to choose a basis, and we have to stick to that basis to explain it.
So let's say gamma is the mass eigenstate, then gamma prime in virtual state. Then what's wrong?
Gamma is the mass eigenstate, and gamma prime is virtual eigenstate.
Just virtual state. So you still have the same diagram.
I'm not quite sure if I'm following the situation, but
just look at Feynman diagram. That's it.
Yes, I'm looking at the Feynman diagram, but that diagram is strictly for the interaction eigenstate. We cannot really bring the mass eigenstate into that diagram. Once we start to talk about the mass eigenstate, we have to replace the whole thing in the right side with a gamma prime that's produced with the epsilon suppression, and that gamma prime decays into photon plus action.
In the mass eigenstate, the Feynman diagram will be like this. So I think it can be possible. And in the mass eigenstate, photon doesn't decay. So you might be confused because this Feynman diagram is drawn in the Flavor eigenstate. So maybe I think I need to change the figure for the mass eigenstate.
Yeah, okay, I'm still confused, but maybe you're right. Okay, thank you.
Any other questions or comments? Okay, I see no more questions, so let's thanks to speakers. Thank you for a very nice talk.